Okay, we're a very small group to start, but we will get started nonetheless. I thought just before we started, I'll show you what I posted on Brightspace this morning. That's the information about the test on Friday. Oh, test 5 information. So our 5th and last test is this Friday. Same deal as last time. It'll be in this classroom. The test, I've got it written. I'm just kind of checking over it one more time to make sure it's really fair and a suitable length. 4 questions, do all of the questions. I'll give you a sheet of equations. That's up on Brightspace now, as is the cover of the test. You are allowed to bring a sheet of notes again. It's kind of a tight number of lectures. Like, I think our last test covered those topics reasonably well. So only lectures 15 through 19. That said, we did cover a fair chunk of material, so those are the topics you could see on the test. That's everything we covered in those lectures. Same study advice is there. Go through the lectures first. Problem sessions is good review. There's some other stuff up on Brightspace. The book is not bad. Please bring your ID, pens and pencils, calculator. You may bring a sheet of notes. You don't have to. If you bring one, single-sided, please, and handwritten. You might find the test a little long. Again, tests can be long, especially where we started this semester giving everybody extra time. And this test is a 50-minute test in 50 minutes. So the timing will feel like the last test felt. So you'll probably have to work briskly as you go. Just any questions before we get into today? Okay, all this stuff is up on Brightspace, and come find me if you need anything. So last day we talked about the magnetic field, which was made by a moving charge or a current carrying wire. We're going to start off today with some examples of that. So we'll do some of the standard examples. And we'll get into some other stuff. So let's say we start. We have 2 long, straight, parallel wires. They're 10 centimeters apart, so here's our 2 wires. If you wish, you can call them I1 and I2. Probably I would do that. They each carry current of 4 amps and in the same direction. So these are 2 wires that look like this, right? So they're parallel, they're sticking out of the page pointing towards you. Find the magnetic field at a point P1, which is halfway between the 2 wires. So here's our point P1. We want to find the net magnetic field right here. So to start this problem, we have to recognize that magnetic field is a vector. We'll have to find the magnetic field vector due to each wire, then we do a vector sum to find the net magnetic field vector. So we're going to follow those steps for the examples that we do. So let's start with the magnetic field from wire 1. We know that magnetic fields make big circles around the wire. So I'm going to start by drawing a circle around the wire. This step of drawing the circles, this step is optional, but it may help you just to get a picture of what the magnetic fields look like. To get a sense of the orientation, we use the right-hand rule. Your thumb is your current. It comes out of the page or towards you. And then your fingers show the orientation of the circle coming around this way, counterclockwise. We're trying to find the magnetic field at point P1, so we specifically have to draw the magnetic field at point P1. We know that it's going to be a tangent to the wire, which you could also think of as perpendicular to the radius. I'm going to go ahead and draw the radius. So this is R1. R1 we know is 5 centimeters. So perpendicular to the radius, or tangent to the circle, is going to give us a line that points either up or down. So the magnetic field here points either up or down. To confirm which way it points, you take your right-hand rule, your thumb comes out of the page, you set your knuckles down where your point is, and you ask, what are my fingers doing? Those tend to point up. They're definitely not pointing down. So our magnetic field at point P1, due to wire 1, points straight up. And it's not a bad idea to get into the habit of showing that that's perpendicular. As we get into some things that aren't sort of all straight up and down like this, we'll want to calculate some angles, so we'll need to remember that those are perpendicular. We found B1, we see that it points up, so we can go ahead and find magnetic field B1 at this point. So the magnitude of the magnetic field is, we'll use the result from last class, mu naught times I1 over 2 pi times R1. Mu naught is our constant 4 pi times 10 to the minus 7 Teslas meters over amps. I1 is equal to 4 amps, that's given. 2 and pi are fine. R1 is your distance between the wire and point P1, 5 centimeters or 0.05 meters. Okay, so those are the ingredients we put into our equation. And that points straight up. At this point in the problem, you could go ahead and do the calculation for the magnetic field. I'm going to hold off for a moment, mostly because I'm terrible on my calculator, and I have an idea that maybe I don't need to do this calculation at all. So if you were a numbers kind of person, you'd probably go ahead and do that calculation, but let's just leave it for the moment. And now let's turn to wire I2. So if we want the net magnetic field, we have to find the magnetic field made by this wire at this point. We know that it makes big circles around the wire. Our right-hand rule shows the orientation of the circles. We know that B2 is going to be perpendicular to R2, which is also 5 centimeters. Perpendicular to R2, and it's a tangent to the circle. So it either points straight up or it points straight down. We use our right-hand rule to figure out. Our thumb goes with our I2 out of the page. Put our knuckles on top of P1, ask what are our fingers doing. Those are pointing down, so this magnetic field B2 points down. So we'll draw our B2. Put in that that's a perpendicular. So now let's write down our vector B2. B2 has magnitude of mu naught times I2 over 2 pi times R2. I2 is the same as I1, equals 4 amps. And R2 is the same as R1, 0.05 meters. B2 points down, so it's the negative J direction. Okay, so there's our magnetic field vector. For our net magnetic field, it just means add them up. So let's do that step next. So our total magnetic field B is B1 plus B2 equals mu naught I1 over 2 pi R1J minus mu naught I2 over 2 pi R2J. Here I notice that my I1 and I2 are the same, R1 and R2 are the same. They point in opposite directions, so my net magnetic field is equal to 0 for this problem. Sometimes on a problem like this, I might ask sort of the flip question. I might give you the two wires and some relevant distances and ask you to find where the magnetic field is 0. So that's where they'd have equal magnitudes in opposite directions. For this one, it's dead in the center. You can imagine if you change, say, the magnitude of I2, it would change where your 0 point was. So that's a typical kind of question. Part B of the question, if we put a third wire carrying a current of 2 amps flowing into the page at point P1, so we're going to put a new wire in here. That current flows into the page, so that's an X, that's our I3. What is the force on this wire? Well, the force on wire 3 is the current in wire 3 times the length of wire 3 crossed with the magnetic field it's sitting in. This one's easy. The magnetic field is 0, so the magnetic force is 0. So this was kind of a straightforward example just to get the gist of the process. We'll kind of ramp it up a notch now. Any questions here? So the next one is a homework example. And in the homework example, I'm going to ask you to find the magnetic field and the force for a point that's out off on one side. I will post the solutions for it. And we'll do another one. Let's keep our same setup. So our two wires, 1 and 2, separated by 10 centimeters. Wire 1, wire 2. Find the magnetic field at point P3, which is 20 centimeters directly above the wire on the left. So it's up here somewhere. Okay, so there's our point. We'll call that P3. We want to find the two things again. We want to find the net magnetic field right here. And if we put a wire here, what will the force on that wire be? Process is the same. Let's find B1, let's find B2. We'll do the vector addition and we'll find the net magnetic field. This time it's not going to be 0. So my magnetic field due to wire 1 makes big circles around wire 1. When you draw your circles, the wire has to be at the center and it has to cut through your point. This is a big circle. I can't fit it all on my page. So it sort of looks like this. Get the orientation with the right-hand rule, so it's coming around like this. Our magnetic field is a tangent to the circle or perpendicular to the radius. There's our R1. 20 centimeters. Perpendicular to the radius looks like this. So it either points right or left. So that's perpendicular to the radius or tangent to the circle. Thumb comes out of the page, knuckles lie on P3, our fingers point to the left, so our magnetic field is to the left. Here is our B1. Here's our right angle. One of two ways, you can go ahead and calculate your B1 now, or you could draw your B2 and then calculate them both together, do calculations at the same time. I think I'll go ahead and do the calculation for B1 now, then we'll have that done, and then we'll go ahead and do B2. So my B1 has a magnitude of mu naught times I1 over 2 times pi times R1. 4 pi times 10 to the minus 7 Tesla meters over amps. I1 is 4 amps. Divide that by 2 pi. R1 is the distance between the wire and the point. That's 20 centimeters, 0.2 meters. So my magnetic field vector B1 has a magnitude of 4.00 times 10 to the minus 6 Teslas. It points to the left, so that's the negative I direction. With the idea that we're going to be doing a vector addition here, I'm just going to go ahead and write down the components of that vector. These components are not that difficult. B1x is negative 4 times 10 to the minus 6 Teslas. B1y equals 0, because it doesn't point up or down. Okay, so there's our magnetic field B1. Any questions? Okay, we'll do B2 next. So the magnetic field around wire 2 makes big circles around the wire, kind of looks something like this. We'll draw that great big circle. My drawing is not the best, yours doesn't have to be the best either, but there's an idea of what a circle is going to be. Right-hand rule gives you the orientation, it's coming around this way. We know that the magnetic field is a tangent to the circle. Here's where the idea that perpendicular to the radius really helps. It's hard to draw the circle. It's hard to know exactly what direction it points in. So here's where the perpendicular to the radius really helps. So here's our radius R2. We're going to be able to calculate R2. That's not going to be difficult. The direction of our magnetic field has to be perpendicular to that R2. So it either points down and left or up and right. The right-hand rule shows our fingers coming down and left. So there's our magnetic field B2. Let's put in where the perpendicular goes. That's between B2 and the radius R2. Are we good here? I know you're in 2055 and you've had lots of practice with vectors. You've been doing it for a long time. I see probably a solid 20% of the class when I give a problem like this, they don't actually do a vector addition. They just add up the magnitudes of B1 and B2. Make sure you're not one of those 20%, so always find your components and remember that you're doing a vector addition. It can be hard to remember it all, but the vector business is pretty important. So we'd like to find B2 as a vector. Let's find the magnitude first, and then we'll go ahead and find the components. The magnitude of B2 is mu naught times I2 over 2 times pi times R2 equals. I2 is 4 amps, that's given. Two and pi on the bottom. We don't know R2. It's not difficult to figure out. We see that that's the hypotenuse of a right angle triangle. The legs are 20 centimeters and 10 centimeters. We can use our Pythagorean theorem to find R2. So R2 equals the square root of 20 centimeters squared plus 10 centimeters squared. Put that through the calculator. We find R2 is 22.361 centimeters. Typically, it's a good idea to keep a few extra sig figs in your workings just so you don't round yourself out of the correct answer. So we'll put this in for our R2. And we get that our magnetic field B2 has a magnitude of 3.578 times 10 to the minus 6 Teslas. You might notice that B2 is a little smaller than B1. That makes sense. It's further away than wire 1 was. Okay, so the magnetic field is going to be a little smaller. So there's the magnitude of our magnetic field. We're doing a vector addition. We want to find the components, so we have to do some work to find the components of B1 and B2. The components of B2, the x component points to the left, there's B2x, and the y component points down, B2y, or you can draw them over here on this side, doesn't really matter. Okay, I feel like I've got as much as I possibly can on that diagram. It's a little bit too full, so I'm just going to grab a separate sheet of paper and start over so that we can find our angle without making that diagram there too cluttered. So there's our point 3, there's our B2, that's our distance R2, there's our wire right here, there's our perpendicular. B2x, B2y is the vertical part. So if we want to find the components, we're going to have to find the angle. The angle I'd like to find will be this one right here. I'm going to call this angle theta. So, something else I'm going to get on this picture. Here is my 20 centimeters right here, 20 cm. Here's my 10 centimeters right here, 10 cm. A lot of these magnetic field problems, they often just reduce to doing some geometry, so try and stay careful when you're doing your geometry. The angle that I've labeled here, theta, this is the one I'd like to figure out because I'll use sine and cosine to find my components. Let's see if I can figure out this angle. So this one I've labeled theta. My B2 and my R2 are perpendicular. So the angle that's in here, say I call that alpha, theta plus alpha equals 90 degrees. Because B2 and R2 are perpendicular. So theta will be 90 degrees, take away alpha. Could I find my alpha? Well, tan of alpha is opposite over adjacent, 20 over 10, 10 over 20. So I think, yes, I could find my alpha. So alpha is going to be the inverse tan of opposite over adjacent, 10 centimeters, divided by 20 centimeters. Alpha is equal to 26.57 degrees. So then my theta is 90 degrees minus alpha. My theta is 63.43 degrees. Is this step okay? All right, now let's find my components of B2. So my B2y, I'll go ahead and label that one now. I'll just come back to my previous slide now to write these results down there. So for my B2x, it points to the left, it's going to be negative. So B2x is negative B2 times sine theta. I won't go ahead and write the numbers in. 3.578 times 10 to the minus 6 teslas times the sine of 63.43. B2x equals minus 3.20 times 10 to the minus 6 teslas. So that's my x component of B2. For my y component, that's adjacent to my angle. It also points down. So B2y is minus B2 cos theta. Put my numbers in there and I get minus 1.60 times 10 to the minus 6 teslas. Good to hear? All right, now we're ready to do our vector addition. We've set ourselves up really well because we did already find the x and y components of the magnetic fields. So let's use those components and let's find the total magnetic field. So the net magnetic field B is B1 plus B2, that's a vector. My x component of vector B is B1x plus B2x. B1x was our minus 4 times 10 to the minus 6 teslas, plus our B2x minus 3.2 times 10 to the minus 6 teslas. So our x component of our net magnetic field is minus 7.2 times 10 to the minus 6 teslas. So there's the x component. I just added the two x's together. For the y component, I'll add the two y's together. By is B1y plus B2y. B1y, that was 0. B2y was minus 1.6 times 10 to the minus 6 teslas. So now I've got my x and y components of my net magnetic field. So I can write my answer as a vector. So my vector B is minus 7.20 times 10 to the minus 6 teslas I, minus 1.60 times 10 to the minus 6 teslas J. Or if you want it to look kind of slick, you might say minus 7.2I minus 1.6J times 10 to the minus 6 teslas. When I personally solve these magnetic field problems, I tend to just leave my answer in unit vector notation. That's a perfectly good descriptor of a vector. Some people prefer the polar notation with magnitude and direction. If you found that, I wouldn't mark it wrong. It's just as correct a way to calculate a vector. To me, it's just more work, so I wouldn't bother. Okay? But either is fine. So if you took this from here and went to polar notation, that's absolutely fine. Okay, any questions? So far, so good. So the third part of our question now, if a third wire carrying current of 2 amps flowing into the page is placed at our point P3, find the net force on it. So to find that, we're going to remember that magnetic force is IL cross B. We're going to pretend that I remembered to put in that the length was 1 meter. And we'll go ahead and find the magnetic force. This one here. I'm going to redraw my picture. So here's our point P3. We're placing a wire with current that flows into the page, I3. I've got my wire I1 here, my wire I2 here. They have currents flowing out of the page. They made that net magnetic field that we just calculated. If you wanted to draw that net magnetic field we just calculated, it would look something like this. It's got a big X component, a small Y component. So there's that net magnetic field. To find the force, we use F equals IL cross B. So the force on wire 3 equals I times L3 crossed with the net magnetic field that it sits in. So wires 1 and 2 make a magnetic field, wire 3 sits in it, so it feels a force. Two options here. We can do magnitude, so I times L3 times B times the sine of the angle between them, and then right-hand rule for direction. Or we can do the cross product. I think I'm going to go with the cross product route. So our current I, we were given that was 2 amps. Our length L3, the length is 1 meter. The direction is into the page. That's the negative K direction. And that's going to be crossed with the magnetic field, which is minus 7.2 I minus 1.6 J times 10 to the minus 6 Teslas. Okay, so there's our cross product. Let's see if we can simplify this a little bit. So I've got 2 times minus 1 times 10 to the minus 6. Outside of K cross minus 7.20 I minus 1.60 J. Okay, so this was just a little bit of algebra. I took my 10 to the minus 6 and I moved it up here towards the front, and I've got my K hat here crossed with my bits of my magnetic field. So I just pulled my 10 to the minus 6 up towards the front, and I put my K hat inside of a bracket. So let's do this next part. 2 times minus 1 times 10 to the minus 6. That's 2 times 10 to the minus 6. Our units are the units for force, so those are going to be newtons. And then I've got so minus 7.20 K cross I hat plus minus 1.60 K cross J hat. So for this next step, I just applied my distributive property. I did K cross each of those terms, and I brought my numbers, my scalars, out to the front of those. K cross I, that's equal to J. K cross J is negative I. Okay, so that's something you should know or be able to figure out. So let's see where this gets us. So I've got minus 2 times 10 to the minus 6 times negative 7.2 gives me plus 14.4 times 10 to the minus 6 newtons J. And then minus 2 times 10 to the minus 6 times minus 1.6. Oh, and then I've got my minus I. Okay, so that gives us a minus. So I've got minus 2 times 10 to the minus 6 times minus 1.6 times minus I gives us minus 3.20 times 10 to the minus 6 newtons I hat. And then typically you just write it with the I first. So there is the net force. If you were thinking about just double checking, did that direction make sense? Because it says it points to the left, negative I, and up, positive J. So our right-hand rule, F is I, L cross B. So your L is into the page, that's your thumb. You're crossing it with your magnetic field. That's hard on my hands, I'm going to twist my paper. So I is into the page, B is this way. My force comes up perpendicular to both of them this way. So that magnetic force comes up this way. Perpendicular. This magnetic force does indeed point up and left. The X component is kind of small, the Y component is kind of big. That matches what we have here, so it makes sense. It's consistent with what we can do. Okay, questions? So we're going to keep working on magnetic field around current loops or current carrying wires, but we'll switch to looking at a loop instead. Okay, so this maybe will ring a bell from when we did the electric field around a ring of charge. We're going to use some similar stuff here. It's not exactly the same because magnetic and electric fields are a little different. So what we'd like to find here is we've got a loop of wire. We're going to put a current in it. Let's say that the current flows around in this direction. So there's our current I. I'm only picking that direction because I've picked some direction, so why not this one? So my current I is coming around this way. I'd like to find the total magnetic field somewhere on the axis, but not at the center. Okay, so that's my goal for this problem. We're going to use our Biot-Savart law to think about this, and we've got our Biot-Savart law written down here. We know that we want to find magnitude and direction, so let's sort out the direction first, and then let's use our equation and we'll sort out the magnitude. For the direction, we're going to use our right-hand rule because the direction of B goes as ds cross r hat. So I think I'm going to try this by drawing a picture on the board. I was going to bring a hula hoop and try and set it all up, but I can't carry a hula hoop to my next class. So I'll draw a circle on the board, and that's going to represent our loop. So instead of having that 3D picture now, the loop is here. Everybody can see that okay, right? And the axis is coming out of the page towards you. So the axis is coming towards you. We're trying to find the magnetic field right here. So some distance from the center out in front towards you. So we need to pick our ds. I'm going to pick a little bit of ds. Our current is coming this way. There's our current. ds means we pick a little bit of the wire, that distance that our charge moved. Our distance is going to be right here, ds. Okay, so there's our picture. We want the direction of the magnetic field right here. Our Biot-Savart law tells us that the direction of the magnetic field depends on ds cross r hat. So if our magnetic field is right here at the center at this point, so our ds is coming this way, our r hat points from the wire, from our ds, to the point where we're trying to find the field. So our r hat points this way. Right-hand rule says ds is this way, r hat is this way, and our magnetic field points up this way. Kind of see that? So our magnetic field is going to point up this way. Good there? So ds points toward that wall. R hat points down towards this point where we're trying to find it. Magnetic field has to be perpendicular to our r hat, and the right-hand rule tells us it has to come up. As we come around the wire, our right-hand rule will always be doing the same thing. Okay? So your thumb just keeps tracing it around the whole way as we go. So can people kind of see that? Okay, we're going to draw more pictures so that we get something in our notes. But that's the idea of what we're using, and that's how you apply the right-hand rule. I'm definitely going to recommend that you're able to do that right-hand rule yourself, too. So I drew my loop 4 times. I guess you can remember that when we did the electric field, we used a lot of symmetry and cancellation. We're going to look for symmetry and cancellation here. We know magnetic field is a vector, it has x, y, and z components. Will any of those cancel due to the symmetry? So that's our question here. You might have an idea already, you might not. Let's see if we can figure it out. For these 2 pictures here, I'm going to ask, is there any symmetry in the y direction? So the first thing I'm going to do is I'm going to pick my ds, my little bit of the loop right at the top. Here's my ds. Trying to find my magnetic field here at point P. My r goes from ds to P. So my r hat is also in that direction. So if we try and use our right-hand rule, ds is this way, r hat is this way, and our magnetic field points up. Right? So ds comes this way, r hat comes this way, and magnetic field comes out this way. So our little bit of magnetic field made by that little bit of loop points straight up. So I guess it points a little bit in positive x and a little bit up. So it's got two components, x and y. The x component is in the positive x direction, dbx. The y component is in the positive y direction, dby. And you should 100% do this for yourself so you convince yourself with the right-hand rule. For the next little bit, I'm trying to ask about cancellation. So this picture shows the ds on the top. I'm going to ask what happens if I pick the ds on the bottom, so sort of the twin on the other side. So if I take my ds on the bottom down here, got to stay in the right orientation, so my current is coming around the wire this way. My vector r goes from my ds to my point. My r hat goes from my ds to my point. There's r hat. ds cross r hat gives me a magnetic field that points down, so right and down. This time dB points down this way. It also has x and y components. The x component is to the right. The y component is down. So what do we think about the y components? They got to sum up to be 0, right? Any place where on the top part of the wire, the y component of the magnetic field will point up. Any place where on the bottom part of the wire, the y component of the magnetic field will point down. When you take the total magnetic field, all the ups and downs will cancel, and the y component of magnetic field will be 0. So y components cancel. And in math terms, that means dy, which is the integral of dby, the sum of all the y bits, equals 0. And that's due to the symmetry of the ring. Everybody okay with that bit? Okay, so now let's do the Z components because they matter as well. Z is definitely harder to draw, but I'll give it my best shot. So I'll take a little bit of my ds over here. ds comes up this way. My r hat comes from my ds towards my point. So there's r. There's r hat. The direction of this magnetic field is a little bit in x and a little bit in negative z. So ds cross r hat gives an answer that comes back this way. And in terms of what we were doing on the board when we had our loop up there, so if the ds was over here on this side, r hat points this way, ds cross r hat gives me a magnetic field that points back this way. Okay, so that's what's going on in the z direction. So my little bit of field dB comes this way. It's in the positive x, dBx. And in the negative z, dBz. So the z directions, if we're on the back half of the loop, all of the z components will point in the negative z. If we're on the front half of the loop, so if our ds is over here, then our r goes to point P, our hat points towards point P, and our dB points positive x, positive z. There's dB this time. Okay. So in the front half of the loop, all of the components of the magnetic field point towards the front. That tells us that the z components cancel. Or dz equals integral of dBz equals 0 due to the symmetry. Any questions? So Do the x components cancel? No, they all point forward, right? So our x's definitely don't cancel. To get those to cancel, some would have to point left and some would have to point right. So the x's do not cancel. Okay, let's go back to our first slide. So on our first slide, we'll add the note that dy equals dz equals 0. That's from symmetry arguments. So then our net magnetic field B will be the sum of all the little x components, dvx, and it will point in the x direction I have. So our net magnetic field is along the x-axis, and it will point in the positive x direction. Okay, so now we're going to have to use some geometry, some trigonometry. We're going to figure out what is dbx, and then we're going to do the integral, and we're going to add it up, and we're going to find our net magnetic field. So let's go to yet another new picture. So a restatement of our problem, find the magnetic field at distance x from the center of a current loop. There's a reminder of our equation and what everything there stands for. So in our equation, or why don't we get everything on our diagram first, actually. So our current, we said, is going to come around this way. So here's our current I. We know that we have to pick a little bit ds because that's in our Biot-Savart law. I'm going to pick a little bit up here. So my ds points this way. I know that r goes from my little bit ds to my point P, so this is my R. My R hat points along this direction towards P. There's my R hat. I've got a loop, it's got radius that I'll call R, so I'll put the radius of my loop from here to here. That's capital R. My distance along the x-axis, that distance is x from here to here. So now my diagram is reasonably well labeled. I think the next thing I'll put in is just an angle theta, because we are thinking about components. So there's my angle theta. I know that the magnetic field made by this little chunk of wire up here points up. So my dB points up this way. And I know that has to be perpendicular to my R right here. So I've got my diagram filled in pretty nicely here. There's going to be lots of things I can find. So theta is going to, from my trigonometry, little r from my Pythagorean theorem. My dB has components, x and y components. My x component points towards the right. That's the one I'm really interested in. My y component points up. Don't care so much about that one because I know in the end it sums up to be 0. Okay, everybody okay with the diagram, where everything is? So let's get going with the equation. My net magnetic field B is going to be my x component in the x direction. My x component is going to be the sum of all the little x components. My dBx, that's a component of my dB, so I know I'm going to need to use sine or cosine to figure that out, just like all my regular vectors. I labeled my angle theta up here. I'd like to figure out what this angle is in right here. Okay, so I want to figure out, am I going to use sine or cosine? Is it going to be theta, or is it going to be a different angle? So let's zoom in on the diagram, make sure we understand where all the angles are going to come from. Right here, I'm not going to draw on top of it because I don't want to mess up the diagram. This is a triangle. All the angles in a triangle sum up to 180. Everybody remembers that from high school. This is a right angle because that's between x and y. So our angle in right here has got to be 90 minus theta. So 90 minus theta plus 90 plus theta gives us 180. So this little angle in right here is 90 minus theta. So say if this was 30, this would be 60. This angle right here is 90 because dB and r have to be perpendicular. So now this is the angle we're interested in right here. This is a straight line, so all of those have to add up to be 180 degrees. So this angle in right here, so that angle is 180 degrees. Take away 90 minus theta, take away 90 equals theta. So this angle is also theta. So there's going to be a fair bit of geometry in this magnetic field section. There's kind of no getting away from it because you always got to figure out those angles. So my dBx is adjacent to that angle theta. It means dBx is going to be dB times cosine theta. This dB right here, you'll notice I am being very careful with my vector notation. This doesn't have an arrow on top. This is not a vector. This is the magnitude of the vector dB. So let's figure out what that's going to be equal to so we can put it in the equation. So our Biot-Savart law tells us something about B. So the little bit of magnetic field, dB, is mu naught over 4 pi times I times ds cross r hat divided by r squared. So that is the vector. To find the magnitude, I want to know what's the magnitude of ds cross r hat. The magnitude of ds cross r hat is the magnitude of ds times the magnitude of r hat times the sine of the angle between ds and r hat. This one feels like it gets tricky. The angle between ds and r hat, so ds is this way, r hat is this way, so ds is a little bit along the top of the loop, r hat is towards you. We're asking what's the angle between those guys? That's 90 degrees. So ds and r hat are perpendicular. When I hold it up like that, it's a little easier to see. So the magnitude of dB then is mu naught over 4 pi times I times ds divided by r squared. Oh, this is a terrible time to stop, but it would be worse if I did like one more minute. Okay, so if you want to, like you can try and go on ahead with this before our next class on Wednesday, see if you can dig into it a little further. That might be good practice. In the meantime, we'll stop there for today, and we'll kind of pick it up in the middle on Wednesday.